Welcome back to ECE 220. Long list of announcements. I will maybe let you read those, but we're finishing up the labs. Group A, your lab number 5 report is due before you think about a recess, but Thanksgiving recess is Thursday and Friday. Before anybody leaves, you need to make sure and submit or complete your homework number 13, which is Tuesday, tomorrow. And Group B, your last lab is actually tomorrow. When we return in 1 week, we will have a review lecture for exam number 4. And exam number 4 is on Thursday, and then we will not have class the following day on that Friday. Today we're getting into the last new component that we'll be playing with in this class, which is an ideal transformer. It's an extension of what you've learned with inductors and mutual inductance. We just take it to the extreme and have our inductances go to infinity, and we have a strong coupling in the magnetic core, and that gives us some properties of an ideal transformer that we will talk about, then some applications, and then we'll get into the details of how we can analyze circuits that involve transformers. We'll look at the voltage ratio and the current ratio and what that means relative to impedances seen across the transformer. And we'll try to work problems. Maybe tomorrow will be all problems so that you can now be prepared for the final exam, which this material won't be on exam 4, but it will be on the final, and it looks like from the previous final, maybe half of the final material might be on the material post exam number 4. I'll look at that a little more closely, but the final is comprehensive, but it's weighted towards the last material, which is chapter 9. That's what I'm seeing from previous semesters. Here's the schematic of the ideal transformer, and we're basically distinguishing it a little bit from coupled cores by these 2 lines, straight lines between the coils, which indicate now we are connected through some kind of maybe iron material as the core material that these coils are wound around. And we'll have a primary side, we'll have a secondary side. We'll try to use I1 or the subscript 1 for the primary, the subscript 2 for the secondary, and the orientation of the dots and the currents and the voltages will make a difference when we start looking at these ratios. The ratios won't always be with positive signs. We actually might have negative signs depending on how the currents and voltages are labeled on our ideal transformer. But with this particular illustration, this one has our turns ratios as positive. If you look at this, you'll see that the positive polarity labels on our voltage are associated with the dots. That means we have a positive turns ratio on the voltages, and our currents are just the opposite. One current is going into the dot, the other one is going out of the dot, and that also signifies a positive polarity or a positive sign on the turns ratio. You could think of, in an ideal transformer, the energy in equals the energy out. There's no losses. And because of that, you can see that the primary is putting energy in and the secondary is taking that energy out. So power in equals power out, or energy in equals energy out, and this now gives rise to our voltage and current ratios being positive. We'll see that as we get further into the discussion. Here are some properties. One is that the coefficient of coupling, when we have two coils that are connected magnetically, then they have this K. Well, in an ideal transformer, that K is 1. It's as strong as you can get, the coupling. And there I'm just indicating where K is coming from. That's associated with the mutual inductance. M is equal to K times the square root of L1 and L2. The self-inductances of the coils is high. In the ideal case, it goes to infinity, both of the self-inductances of each coil. And as I said, we are not going to have any losses in these coils, so if we were trying to model those, we wouldn't worry about the resistance of those coils. So R1 and R2 are 0. Let's look at some basic equations. We can play with this. If you go back to our diagram, this is what we're now referring to. And in the time domain, the voltage on the secondary, if those terminals are open, what will you see across the secondary coils? It will be a voltage induced by the primary side, or V2 is equal to M di1 dt. The time rate of change in the first coil is mutually coupled to induce a voltage in the second coil. What if we take that into the frequency domain or perform our phasor transform on that particular equation? What do we obtain? What is V sub 2 phasor equal to? If it was MI, it would just be MI bar. But we actually have a differential relationship on the current, and how do we, or what corresponds to differentiation when we go into the phasor domain or through the phasor transform in the frequency domain? What do we do? M comes through, but now how do we transform di1 dt into the frequency domain? Multiplication by j omega. So now we have this j omega I1. And if we simply associate or move things around a little bit, we can now see that V sub 2 is an impedance away or related to the current in coil 1 through an impedance, j omega m. Or it's 90 degrees away from the phase of I1. Likewise, V1, the self-induced voltage, V1 is L di1 dt. What does that transform into? Similarly, we now have L times j omega I1, or this is now j omega L I1 bar. Again, this is now an impedance, and do you see a connection between V2 and V1 relative to they share the same current phasor, and that phasor current is transformed through the same angle because we have a J on both. V2 then is 90 degrees away from the phase of I1. V1 is likewise 90 degrees away from the phase of I1. And because of that, then we can conclude that on this ideal transformer, the voltages on either side, the primary voltage and the secondary voltage, are in phase. If you wanted to sketch a phasor relationship, here I'm showing that the transformer is actually stepping up or increasing the voltage on the secondary relative to the voltage on the primary with the length of the phasors, V1 and V2, but they are both in the same direction and they are 90 degrees ahead of, or they lead, the current phasor in coil 1. That's the relationship of this ideal transformer. If you were practically looking at this, then it's very close to the ideal. One is with these iron cores, or this ferromagnetic material in the transformer that's the coils are wrapped around. That produces a high permeance, which we didn't define or discuss earlier, but you had to play with it in one of your homework problems, I believe, when you had to talk about turns ratio. Now we are going to worry about the turns on each of these coils. On the primary side, that will be N sub 1. On the secondary side, the number of coils that are wrapped around that core is capital N sub 2. And permeance is just a property of converting N1 I1 or N2 I2, the amp turns quantity, into the flux. And if the permeance is high, then the flux is huge. That's sort of the takeaway. And remember, K in our mutual inductance expression is 1. And here in the practical transformer, it's pretty much 1 because of the high permeance. Also, because the permeance is high, that's this funny P symbol, our self-inductance is high. We said in the ideal case it's going off to infinity. In reality, it's pretty high. N squared times a high permeance P. And this iron material-based core of our transformers, they're very efficient, which allows for almost ideal power in equaling power out. We lose a little, which means that maybe the transformer might be a little bit warm, but it's not going to be hot. Anytime we're losing power, usually we're having to get rid of that in some way, and a lot of times it's through I squared R losses, and that really is just dissipated as heat. So anytime you're trying to be efficient, you're trying to minimize the amount of heat you're having to get rid of in your circuit or device. And that's what you're going to be faced with throughout your career, is trying to improve in efficiency and basically minimize the heat generated by those devices. Which means that 30 years later, for example, the ECE building was designed assuming you had these huge computers maybe in your office, and they were producing quite a bit of heat. So in the winter time, you didn't really need a heater in your office. And we just have these little panels in the ceiling, and they don't produce much heat. but now we're much more efficient with our computing equipment, and so we don't have so much heat being generated. So now everybody has their little plug-in heaters near their feet to stay warm in the ECE building. Anyway, we don't get hot with these transformers, and we don't stay very hot in the ECE building. Just saying. What are some applications? Here's one that you'll need to, we'll work through the details, but this one we will be able to analyze a lot, and you'll have probably a problem or more on the final, is how do you select the turns on the primary and the secondary such that you can match the load impedance to the source impedance. And we can do that by the selection of N1 and N2. And we'll derive the equations that allow us to do that. But one application of transformers is impedance matching. A second application, and this actually has multiple, and we'll maybe get into more of those, but here's one relative to isolation. A transformer works because of alternating waveforms. A transform won't work for DC signals. And for that reason, if you have DC signals in the first stage of an amplifier, that's going to be not transmitted. It will be isolated from the second stage. And all you will have is the AC, or the alternating sinusoids, on the secondary side, or at stage 2 of this amplifier circuit. And the one that you probably are or were anticipating is power distribution. You have some kind of generating plant, nuclear, coal, hydroelectric, whatever. Now that's generating power, and you want to get that across the state, across states, across the nation. You're trying to minimize losses. And losses are I squared R. So if you can reduce I, you can potentially reduce the losses of that power during the transmission process. Transformers, if you step up the voltage, you now have these high voltage transmission lines. You haven't changed the power. You've increased the voltage, so you've lowered the current. So the same amount of power can be transmitted. It's just now the I is less to get the same amount of power. And because of that, now you don't have as much loss in the transmission lines due to I squared R losses. Well, we don't have hundreds of thousands of volts coming into our house, thankfully. They step it down, and they step it down several times. Here I'm just showing sort of the first step down, but to get to from the subdivision or the substation, you usually have some kind of, maybe it's buried or maybe it's on the ground somewhere, but you have another transformer that then steps it down further, so that we only have what going into our house here in the United States. And we'll talk about this sometime. We'll have to figure out how to transform what we've been using, which are these maximum voltages, to an RMS value, but we usually refer to these outlets in RMS units, and that's 120 volts roughly. The peak to peak, or the amplitude of those waveforms, are higher by a square root of 2 than the 120. And we'll maybe derive that, but it is in the textbook. If we don't get there, if you're working homework problems over the break or over the recess, you might want to just read that little section in chapter 9 that talks about RMS, or root mean squared. How do you convert any periodic waveform into an RMS level? Or what's the effective voltage? So let's now get into some analysis dealing with ideal transformers, and in particular the voltage ratio and the current ratio on, or relating, the primary and the secondary side of these transformers. First, let's look at the voltage. What is the secondary voltage in this particular setup? Is there any current flowing on the secondary side? It's open. How are we going to get voltage on the secondary? Through the mutual inductance, and that's based on I1, and it's coupled through the mutual inductance. So V sub 2 is J, whoops, I don't really want to be red. J omega M I1. On the primary side, what's the current I1 bar? If you did a KVL, or in this case it's really KVL and only involves one element, it's Ohm's law. V is equal to Zi, and Z is J omega L, so I is in fact V1 over J omega L1. If we now use that relationship or expression for I1 into the first equation, we can now see that we have J omega M times I1, which is V1 over J omega L1. The J omegas cancel, and we're left with then with M over L1 V1 relating V sub 2's phasor with V sub 1's phasor. In an ideal transformer, though, we know this mutual inductance has K equal to 1. It now becomes just the square root of L1, L2. If we do that substitution in our expression for M right there, now we have V sub 2's phasor is equal to the square root of L1, L2 divided by L sub 1. Now if we put everything underneath the radical, we have V sub 2's phasor is equal to the square root of the quotient L2 over L1 times V sub 1. And when K is equal to 1, all that flux that links coil 1 also links coil 2. The permeance, remember, was high. The permeance is the same in both, and the inductance L1 and L2 are simply, what did I say first? L1 is N1 squared P, and L sub 2 is N sub 2 squared P. We put those in the expressions for, or we replace L2 and L1 in our expression for V2's phasor and V1's phasor relationship. Take the square root, the positive square root, and we see that we now have this turns ratio connection between the primary side's phasor voltage and the secondary side's phasor voltage. We now see, and I like to actually kind of think of it, I confuse myself in trying to remember V2 over V1 is equal to something, or I2 over I1. Here I just try to remember that the volts per turn are the same on either side of the transformer coil. So here you have equal, and whoops, and maybe I should emphasize the fact that this is a magnitude. There's going to possibly be a sign change in there depending on how the dots are related to the labels of V1 and V2. But we have an equal volt or volts turn ratio on secondary and primary. You could then solve for, and we'll be trying to connect V sub 2 and V1, so you can see then that sometimes we might write V sub 2 is N2 over N1 V sub 1. If we need to go back and forth, replace V2 with V1 or vice versa. We now have a relationship that allows us to do that. That's now the turns ratio relationship for these voltages on the primary side and secondary side. If we wanted our transformer to step up the voltage, step it up from the primary to the secondary, we would want more turns on the secondary side. N2 would need to be bigger than N sub 1. If we were reducing, and now if you had your wall wart, which now we don't even have those anymore. Do you even know what I'm talking about? Those larger plugs that we used to put into the outlet, those had a transformer in them, and those were step down because you're now powering a lower voltage device. Now that means that on the secondary coil you have fewer turns than on the primary coil side. That would be called a step-down transformer. The up and the down refer to the voltage levels. And current goes just in the opposite direction. With a step up, then your current is going down, and with a step down, your current is going up because the power stays the same. That gets confusing, so just when you're saying step up and step down, know that you're referring to voltages. Let's now look at the current ratio. And to do that, we need to get a current in the secondary side. Let's then short the secondary to produce a current in that side or relative to the secondary coil. And if we now have coils on both sides, we have voltage now on the secondary side due to not only the self-induced or the self-inductance, but also the mutual. And how do we introduce the mutual inductance with its polarity on the secondary side? Now we use the dots, don't we? We simply say, oh, if I1 is going into that dot, now we put a plus on the dot, and this is now j omega m I1. So we have really this series connection of voltage drops on the secondary loop. So let's just do a KVL relative to those. We have I sub 2 going in the clockwise direction now, and it's actually going to be, what's its voltage drop? Going through j omega L sub 2. So now we're doing KVL around So my drawing is a little bit confusing, but we have basically two voltages one due to the self-inductance and one due to the mutual inductance. And I've indicated the sign of the mutual inductance. I haven't really labeled the self-inductance sign, but it's due to the passive sign convention. It will be this polarity labeling. Or KVL now says that we have J omega L sub 2 I sub 2 minus J omega M I sub 1 is equal to 0. That's on the secondary side. That's KVL on the secondary side. This now gives us a relationship between the two currents, the current in coil 1 or on the primary side and the coil on the secondary side, I sub 2. Or we now have J omega L sub 2 I sub 2 is equal to J omega M I sub 1. The J omegas can cancel, and again, knowing that K in an ideal transformer is equal to 1, now we can write M as just the square root of L1 times L2. Re-expressing the inductances in terms of the permeance cancels. It's high, and it's the same in both coils. And now we get a different, in a sense, relationship between the current phasors and these turns on the coils. Now I sub 2 over I sub 1 is in fact N1 over N sub 2. And again, I sort of like to just think in terms of amp turns being equal. Because I get confused, or I confuse myself. Oh, is it N1 over N2? Is it N2 over N1? It's just the opposite of what the voltages were in terms of their relationship. But now we have, and again we have to worry about the magnitude, but you can see that the amp turns on the primary side, I1 N1, is the same as the amp turns on the secondary side, I2 N2. Then you can do the solving that you want depending on which particular current phasor you're trying to maybe eliminate. But the amp turns are equal. And here is a very wordy way of trying to keep track of the signs, but hopefully it will make sense and it will be fairly clean. But now we need to make sure that we are, when we do relate I1 to I2, we need to make certain we have the correct sign relative to that turns ratio. We know the ratio, or we know that the amp turns are equal. Now we want to know what's happening with the sign. So it's based on the dot convention. Here's the positive sign, and now I'm going to confuse you more because I think on the currents I start with the, I don't know what I start with. We'll find out. Okay, so blue. If the coil voltages V1 and V2 share the same polarity label on each dot. So let's say V1 has its positive polarity on the dot and V2 has its positive polarity on its dot. Then the turns ratio has a positive sign. We just say V2 over V1, and again I've confused myself, is equal to N2 over N1 without a reversing of signs. However, if one of the dots has a positive label and the other dot has a negative, then we have to introduce a negative sign on this turns ratio relationship, on the primary and secondary voltages. Here, what I'm trying to say is, for example, in our turns ratio relationship, over V2 over V1, we would now say, oh, that's minus N2 over N1. We would need to introduce a negative sign. Currents are just the opposite. If the coil currents, I1 and I2, are both into the dots or both out of the dots, then that turns ratio is negative. And maybe you can keep this straight another way, is saying power in equals power out, and go back to the original template that we started today's class with, and saying, oh, in this scenario, the way the currents are labeled and the voltages are labeled, all my ratios have a positive sign. Here, if one current enters a dot and the other current leaves a dot, then the turns ratio is positive. All right, enough for all the terminology and the relationships. Let's try to work some problems. Let's do impedance matching. Suppose now we're given the following circuit. We have a Thevenin source, a V sub S, with its impedance, Z sub S, and we now want to know, what does that C? And you could maybe say now, oh, here's AB, or I want to know, what is the impedance seen looking into nodes A and B in this circuit? It's now looking in to the transformer's primary side, and actually what it sees is the reflection of that load through the transformer. So the load impedance looks different than just Z sub L. We can't just arbitrarily remove the transformer. That now influences how Z sub L appears or looks to the primary side. So let's now see if we can figure out Zn or Z sub AB. What are our ideal transformer ratios? Or how do I want to do it? I want to say V1 over N1 is equal to V2 over N2. That's how I like to remember it. My volts per turn are the same on the secondary side and the primary side. V1 over N1 is V2 over N2. Now, what's the sign? Plus or minus? Was my description clear enough for you to answer that question? Do I put a minus sign or do I put a plus sign in that voltage ratio expression based on the way that I've now labeled V1, V2 in this circuit that possesses the ideal transformer? How many think I need a positive sign? How many think I need a negative sign? How many aren't thinking yet this morning? We're okay with our sign because now we're looking at, for voltages, if the polarity labeling on the dot is the same on secondary and primary, then we retain a positive sign on our ratio. So in this case, we're good with that plus sign because we had the same polarity. But I hope it's clear now that before you get too far in, You need to kind of make sure you keep track of what the sign is on that relationship. What about and here then we could say, oh, if I needed to, which I'm going to, do you see that Zn, I could find that as the ratio of V1 over I1? Zn, or Z sub AB, is just going to be V1 phasor divided by I1 phasor. Those phasors ratio will give me an impedance, and that's Zn. I now need to find V1 and I1, some relationship there with Z sub L and these turns ratios. Well, one of those might involve V1, obviously, since I'm taking V1 divided by I1. And what's Z sub L? That's Ohm's law. That's just V sub 2 over I sub 2. So we want to be able to now find something that involves the ratio of the V2 phasor over the I2 phasor and the V1 phasor over the I1 phasor. V1 in terms of V2 is now N1 over N2 V sub 2. That we'll be able to use. What about the current ratio? That was our amp turns are equal on the primary side and the secondary side. What's my polarity on this? Is it plus or minus? Relating I1 and I2 based on my previous description. To have a positive sign, what do I need? I need one current to enter a dot and the other one to leave a dot. Here I have I1 going in and I2 is actually coming out. So again, this turns ratio relationship between for my currents also possesses a positive sign. So I had one entering and one current leaves. I hope that description is clear. And now I can solve for I1. I1 is now equal to N2 over N1 I2. And Zn, which is Z sub AB, is now V1 over I1. But V1, now we have an expression for that. That's N1 over N2, V2. I1, we have an expression for that. That's N2 over N1, I2. We know V2 phasor over I2 phasor is Z sub L. And N1 in the basement of the basement comes upstairs. We now have N1 squared over N sub 2 squared, scaling V2 over I2. That's just Z sub L. So now we know, and Zn is now N1 over N2 squared Z sub L. Or you might hear this referred to as the reflected impedance. And someone might refer to the N1 over N2 or the N2 over N1 as your turns ratio. So let's now rewrite this as 1 over N2 over N1 squared Z sub L. And if we define alpha to be N2 over N1, which is our turns ratio, and I probably won't remember how alpha is defined. That's why I like to just keep track of N1 and N2. But alpha now is the ratio of the secondary coil turns to the primary coil turns. Then we can say that our reflected impedance, or our transformed, and in fact it is a transformed, it's gone through the transformer, our transformed impedance as seen by the source has been the original load impedance divided by alpha squared. So whatever your turns ratio is, you square it, divide that into Z sub L, and that's what is seen at the source. Or the equivalent circuit of the transformer load combination, we can now redraw that. Here is our Thevenin voltage, V sub S. Here is our Thevenin impedance, Z sub S. But now, connected to that, or transformed through the transformer, is now Z sub L over alpha squared. Which we were calling Z sub N. And now you can analyze this circuit. This circuit is a straightforward application of Chapter 9 material. If you need to define the current in the primary side, now you can do that. You've now effectively removed your transformer and replaced the load with its reflected impedance in the equivalent circuit. Or another way of saying that is the ideal transformer secondary coil reflects the load impedance, which was Z sub L, back to the primary coil through this scaling factor, or with a scaling factor one over alpha squared, where that alpha squared, or alpha, was our turns ratio. So now we can, with a transformer, match this load impedance to our source impedance by the appropriate selection of turns on the primary side and the secondary side. And I know this is against my norm, but we'll just stop at that point, and we'll pick up with examples, more examples of how to play with, or not play, but analyze transformer circuits tomorrow.